So I got a few requests to do a video on thermal physics. So I'm doing two of the questions from the textbook that Mr. Wang assigned us. First one is a 6.0 times 10 exponent 2 gram sample of water at 90.0 degrees Celsius leaves mixed with 4.00 times 10 squared grams of water at 22 degrees Celsius. Assume no heat loss to the surroundings. What is the final temperature of the mixture? So to solve this, we first need to say that we need to realize that the heat lost by the 90-degree sample is equal to the heat gained by the 22-degree sample. So to express this in an equation, we do m, I'll just put 1 and 2 to show that they're different, m1, c1, and then delta t1 equals m2 c2 delta t2. So now we also need to put a negative sign in front of one of them, because one of them is the heat lost, so the energy would be negative. One of them is the heat gained, so the energy would be positive. So if we say m1c1 delta t1 is our 90-degree sample, it'll lose heat to match with the 22-degree sample. So we need to put a negative in there so that it'll be positive and equal to the one that gains heat. So the mass of this sample is 6.0 times 10 squared grams, and first we need to convert that into kilograms, so that is 0.60 kilograms. And then the latent C, which is latent heat, I didn't write that down here, but it's right, or not latent heat, specific heat, for 180 joules per kilogram degree Celsius. And if you're wondering where I got these values, they're in the textbook, but they don't say them in the question, in case you want to try them for yourself. Okay, so now we need delta T. So what we're looking for is the final temperature. And to find this, we need to do, excuse me, we do the temperature final minus the initial temperature. And in this case, it's 90.0 degrees Celsius. So now we can work on the other side. M2 is, I think it was 4 times 10 squared grams, and that is 0.400 kilograms. Then we multiply this by latent heat, which is the specific heat, which is the same as the other side, because they're both liquid water. Joules per kilogram degrees Celsius. Then multiply that by same thing as other side, TF, and then do minus the initial temperature for this sample, which is 22 degrees Celsius. So now we just have a really long line equation. So we should try to simplify this a little first by multiplying the two first expressions. So 0.6 times 4180 is 2508, and with a negative. And for the units, the kilograms cancel out, so it's just joules. Give me 1 second. Joules per degree Celsius. And then we multiply by TF minus 90.0 degrees Celsius. Oh, and for the sig figs, there's 2 because of the 0.60. And we have it make it equal to the other side. Do the same thing. 0.4 times 4180 equals 1672. Oops. And then we also, same unit as last time. Kilograms cancel out, so it's joules per degree Celsius. And the unit, the sig fig is on the 7. We multiply by the same thing. Minus 22 degrees Celsius. Okay, so now we have a smaller equation, and all we can do now is distribute the front term to what's inside the bracket. So we get negative 2508 joules per degree Celsius times TF, and minus, multiply the 2508 times 90, we get 225720. Oh, and the negatives cancel out, so it's positive. 225720. And the unit is joules because the C's cancel out. And for the sig figs, this one has 2, this one has 3, so we make it have 2. And then do the same thing on the other side. We get 1672 joules per degree Celsius. Then multiply by TF. Then minus 22 times 1672. You get 36784. 784. And the C's cancel out again, so it's just joules with 2 sig figs. Oh, oops. Because of the 22 degrees Celsius. Now we can move the terms over on each side, so that on one side we have the TF, and on the other side we just have the joules. So I'll subtract this one over, this TF over to this side. So negative 2508 minus 1672 equals negative 4180. Celsius times TF. And then this one has a sig fig on the hundreds, this one is on the tens, So the least precise is the hundreds, so we rounded up to the 1. And then equals, we take this number and subtract this number from it. So negative 367.84 minus 225720. We get negative 262.2504 joules. Since we have a negative on both sides, we can just erase it. Multiply both sides by -1. And then finally, we can do TF equals this, our joules divided by our joules per degree Celsius. So 2504 divided by 4180 equals 62.8. And I forgot to do the sig fig on this number. So it's 1, 2, 3, 4, 5, 10, or 100,000. No, 10,000. And this one is the thousands. So we rounded up to the 10,000s. 1, 2, 3, 4, 5. This one. So this one has 2 sig figs divided by something else with 2 sig figs. So this one should have 2 sig figs, and we rounded up to 63. And also when we divide the two sides, the joules cancel out, and the C moves up to the top. So all we have left is degrees Celsius. And that's our answer. Now for the next question. How much heat is added to a 10.0 gram of ice, I think it should say sample, at negative 20.0 degrees Celsius to convert it to steam at 120.0 degrees Celsius? So this one is a lot more complicated than it seems. I'll first start by drawing a graph to help show what is happening. So when you're heating the ice, it goes like this. Here, I'll draw the axes first. We have this and this, and we say this one is temperature, degrees Celsius, and this one is energy, thermal energy, and this is in joules. So first we have ice, and it is going up like this at a constant, with a constant relationship, but then it begins to melt, and when it is melting, there's a plateau which looks like this. So the temperature does not increase, but the energy is still increasing, and then it completely melts. There we have water now, and then water has its own relationship, which is like this. And then when we hit 100 degrees Celsius, it turns into steam. Here, let me write these. This is 0. This is 100. So it turns into steam and hits another plateau. The energy is increasing, but the temperature is staying the same. And then it goes up, when it is steam, it goes up again for another 20 degrees because it heats up to 120. So like that. So here there are 1, 2, 3, 4, 5 different parts we have to calculate. And then to find the total heat added, we just add up every single horizontal distance for each of these sections. So to start, we'll do the first part, this right here. So to find this, we need to let me see. We need to use the formula E equals mc delta T. Since we have the specific heat and also the change in temperature and also the mass. So we take the mass, which is 10 grams. If we change that to kilograms, we get 0.0100 kilograms. 0100 kg. We should probably rewrite that. And then for the latent heat, or no, the specific heat, we're given that. It is C for this one. Water specific, ice specific heat, 2060 joules per kilogram degrees Celsius. 2060 joules per kilogram degrees Celsius. And I'll erase some of our previous work. And then for the last one, we do delta T. So that is what we got. What we're given is it starts off at negative 20 degrees Celsius, and we do until it starts melting, and water melts at 0 degrees Celsius. So it's negative 20 minus 0, or no, TF minus TI. So TF is 0 degrees, minus TI is negative 20 degrees. So 0 minus negative 20 degrees is 20 degrees Celsius. And then we just expand everything. 0.01 times 2060 times 20. We get 412. And the unit, the C's cancel out, and the kilograms cancel out. So we're left with joules. And it has 3 sig figs, so we don't need to do anything. I'll underline these values. So next, we're on this part right here. So when you have a plateau, when it is changing states, the temperature is not going up, but the energy, in this case it's the potential energy that's going up. So to calculate how much energy we gain, we use the formula E equals mL, where L is the latent heat, or in this case the ice heat of fusion. So we have mass, it's the same in every calculation, 0.100 kg, and multiply that by 3.344 times 10 exponent 5 joules per kg. So the kilograms cancel out, and we're left with 3.34 times 10 exponent 5. That's 334,000, and then we multiply by 0.01. We get 3,340. Joules. And this one has 3 sig figs. So next, we're calculating this part right here. And you see, if it's on an angle, then that means you use the formula E equals mc delta t. If it's on a plateau, we use the formula E equals ml. So in this case, it's slanted, so we use E equals mc delta t. C delta t equals so m, same as always, 0.0100. We never lose any mass or gain any mass. It's the same sample. And then C, the specific heat for water is 4180 joules per kilogram degree Celsius. Then multiply that by delta T. So we see it's going from 0 degrees to 100 degrees. So the delta T, it's going up 100 degrees. So it's 100 degrees. And I think it's 100.0 degrees Celsius. So cancel out the degrees Celsius, cancel out the kilograms, we're left with joules. And this is these two. This is divide by 100. It's the same thing, and this is 100. So those cancel out, and it's just 4180 joules with 3 sig figs. Then the last two, we're at another plateau, so we put E equals ml. L equals m, same as always, 100 kg. Then multiply that by the latent heat, or in this case, water heat of vaporization. I'll expand it first before I write it. 2.26 times 10 exponent 6 is 2,260,000. 260. And the unit is joules per kilogram. And then the kilograms cancel out. So we multiply this by 0.01. We get 22,600. And with 3 sig figs again, joules. Now, last one finally. It's slanted, so we use the formula E equals mc delta t. So m 0.01, and then C, let's take a look, specific heat, which is, and we're at steam right now because we passed 100 degrees for water, so it's 2020 joules per kilogram degrees Celsius. Okay, and then multiplied by delta T. So right now we're at 100 degrees, and it goes up to 120. So it goes up 20 degrees. 20.0 degrees Celsius. Then we can just multiply everything. 0.01 times 20 times 20. Okay, 404. And with 3 sig figs again. And now all we need to do is add up everything here. So E, let's do total, T for total, equals 404 plus 22600, and go back up, plus 4180 plus 3340 plus 412. We get E equals 30936 joules. Now we need to check the sig figs. So this one is on the units, this is on the hundreds, tens, units. So hundreds is the least precise, and for us the hundreds is the 9. So we do 30,900 joules. And that's it. This question takes a very long time, but it's not too hard if you think about it. Just the same formulas over and over again. So that's it. Thank you for watching.